Let's move to the kernel nullity of a 3 by 3 matrix. Here, we are going to solve for the kernel or the set of all vectors v, which could satisfy a linear transformation in this manner. A linear transformation of vector v is equal to the product of this matrix, with the same matrix here as well, times a certain vector v equal to a 0 vector. So we're going to solve for all possible values of vector v here. Now, we need to understand that this is a 3 by 3 matrix. So m by n. So it's actually safe for us to say that our transformation is this one here. We don't need to worry. This is still R3 to R3. My point of sharing this is that our 0 vector that will be used there is 0 vector in R3, and the set of vectors v are also element of R3, such as v sub 1, v sub 2, and v sub 3. Now, while this is not an issue here, this might be an issue on other form matrix such as non-square matrix, so that it would be very important to start with this. Well, anyway, again, the set of vectors v that we're going to solve here are a set of vectors in this form, and a 0 vector is a vector on R3. To do that, we can always pair our vector A with our matrix A with this vector V. But to make it easier, let's come up with the reduced row echelon form of this matrix. Okay, we can do that by here. We have 2, 1, 3, 1, 1, 0, 0, 1, negative 3. Of course, you could always multiply 1/2 to the first row, but what I would like to do here is to interchange the entries of row 1 and row. Once we interchange them, we have this matrix. We have 1, 1, 0, 2, 1, 3, 0, and 1, and negative 3 here. Now let's try to multiply negative 2 to row 1 plus row 2 for a new row 2 to make this 0. Okay, so we'll have this connection here, 1, 1, 0 still. You will have negative 2 times 1, negative 2 plus 2, 0. Negative 2 times 1 is negative 2 plus 1 here is negative 1. This is still 3. So 0, 1, negative 3. Right? Next is to multiply negative to row 2. So this would be a leading 1. Row 2. So you have here 1, 1, 0, 0, 1, negative 3, 0, 1, negative 3. Notice that we have 2 rows of the same entries. You would actually expect later rows of zeros. But to continue, let's make this 0. We'll have here negative of row 2 plus row 3 to have a new row 3. So you have 1, 1, 0, 0, 1, negative 3, 0, of course, negative 1 plus 1, 0, positive 3 plus negative 3 is 0 here. To finish, let's make this 0. See that we have here a row of zeros because we have rows of the same entries. But our goal is to have a reduced row echelon form. Let's make the 0. So we'll have negative row 2 plus row 1 for a new row 1. We have here 1. So okay, let's try to copy at the bottom. This is 1, negative 3. Negative 2 times negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times negative 3 is positive 3 plus 0. You have here 3. Alright. This is now the reduced row echelon form of our matrix A here. Now let's try to multiply this with a certain vector, this vector in R3, and equate to 0 vector in R3 as well. And we will have this, v sub 1, v sub 2, v sub 3 equal to 0, 0, and 0. Once you multiply that, or before you multiply that, notice that our vector 3 here doesn't have an exact value, right? So we can actually choose a specific arbitrary constant to represent rather our x sub 3. So let x sub 3 be equal to t. Okay? And with that, as we multiply the first and second rows here, you will have v sub 1 plus 3 v sub 3 is 0. You also have v sub 2 minus 3 v sub 3 equal to 0. Since we already have this, this second equation here, we have v sub 2 minus 3t equal to 0. V sub 2 is equal to positive 3t. And this will become v sub 1 plus 3t equal to 0. V sub 1 is equal to negative 3t. So our vectors here are expressed in terms of t. In short, the vector, the set of all vectors here, the vectors as ones can be represented as negative 3t, positive 3t, and then t. Or, if we're going to take out that, okay, we'll have this kernel now. The kernel of t. As you take out t, okay, you will have your negative 3, 3, and 1, such that t is an element of a real number. This is now the set of all vectors, since you have an arbitrary variable t which could take any value as long as it's a real number. However, the nullity of t is equal to the dimension of the basis of the kernel, which means there's only one here. Okay? So the nullity of t is equal to 1, as we only have one vector in this set of kernel. Of course, there are a lot since there are multiples of t, but we have only one here basis. So we only have one. Okay? So that's the nullity of t. Let's duplicate the process here for the second. Again, before we use this, let's come up with the reduced row echelon form of this. So we have here 1, 1, negative 1, 1, 2, 1, 0, 1, and then 0. Let's make the 0 by multiplying negative 1 to R1 plus R2 to have a new R2. Row 2 rather. 1, 1, negative 1. This would become negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times 1 is negative 1 plus 2, 1. Negative 1 times negative 1 is positive 1 plus 1. I have here 2. 0, 1, 0. Since it's already a leading 1, let's make this 0 now. So we're going to multiply negative 1 to R2 plus R3 for a new R3. Row 3 rather. 1, 1, negative 1. 0, 1, 2, still 0. Negative 1 times 1 is negative 1 plus 1, 0. Negative 1 times 2 is negative 2 plus 0, you have negative 2. Of course, we can multiply negative 1/2 to row 3. So this would be a 1. Okay. Leading 1. 1, 1, negative 1. 0, 1, 2. 0, 0, and then 1. Next, working backwards. Let's make the 0 and 0 because our goal is a reduced row echelon form, as this is still a row echelon form. So we have negative 2 of row 3 plus row 2 to have a new row 2, and then simply add row 3 and row 1 for a new row 1. So this is 0, 0, 1. We're working backwards. 0, negative 2 times 0 is just 0 plus 1 is still 1. Here, negative 2 times 1 is negative 2 plus 2, 0. This is still 1 here because you're going to add 0 plus 1 is just 1. 0 plus 1 is also 1. 1 plus negative 1 is 0. Finally, let's make this 0. So negative of row 2 plus row 1 for a new row 1. Okay? You have here 0, 0, 1, 0, 1, 0. So negative 2, negative 1 times 1 is negative 1 plus 1, 0. Here, 0, 0 is a 0. Now we have reached this reduced row echelon form, and just like earlier, we're going to multiply here v sub 1, v sub 2, v sub 3, and equate it to the 0 vector in R3. Notice that we have exact, or these are the standard vectors for this 3x3 matrix. And if we're going to multiply that, v sub 1 is 0, v sub 2 is 0, v sub 3 is also 0. Hence, the vector here, which could make our first matrix under this linear transformation be equal to 0 vector in R3, is also the 0 vector in R3 itself. This would mean that the kernel of T here is a set containing the 0 vector in R3. However, the nullity of T is the dimension of the basis of the kernel. And since our kernel of T contains only the 0 vector in R3, it has no basis. Hence, the nullity of T is 0. We don't count this as 1, right? So nullity, kernel. This is for the second matrix. So this is how we solve the kernel nullity of linear transformation involving 3 by 3 matrices. Thank you very much for watching.